G'day, welcome to the first video in a series of videos which will cover Module 5, Advanced Mechanics. This is the first module for the Year 12 component of the course in physics and builds on content and concepts that we have learnt previously, primarily in Module 1 and 2. What we'll be covering in this first video is introducing concepts around projectile motion, which is the body for our first inquiry question, and look at trying to determine the initial velocity of a projectile. The content in this video will help us to cover dot points 5.1, 2, and 4. While the content of this video doesn't directly address any of the key dot points, it will set us up to be able to tackle inquiry question 1 as a whole, which focuses on projectile motion. So our learning intentions for today is to first define a projectile, then introduce the concept of projectile motion, and apply some basic principles from Module 1 to determine horizontal and vertical components of a projectile in motion. So first off, projectiles and projectile motion. A projectile is defined as an object which is launched through the air. This may mean that it is thrown, fired, or flung. When we apply a force to a projectile, it's only given at the point of launch. What's assumed is that the projectile does not have any form of constant applied force. The only force that is being applied is that initial force that actually gets the object to launch at its launch point. When we try to show the path traveled by the projectile and its motion, we usually call this the trajectory. In this course, we're going to assume that the trajectory of a projectile in motion, no matter what it is, follows some form of parabolic shape. Within the scope of this inquiry question, we're going to be looking at trying to determine many behaviors and characteristics of a projectile in motion. These include initial velocity, velocity at a given time of flight, the maximum height, the distance traveled, all that kind of stuff. So when we are looking at the trajectory of a projectile, there are a few things that can influence the path taken by the projectile. First off, the initial force applied and therefore the velocity applied to the object, the angle at which the projectile is being launched, and acceleration due to gravity are all really influential on the motion of a projectile and its resulting trajectory. Air resistance is also a key factor when analysing projectiles and how they behave. However, in the scope of this course, we will assume that there is always no air resistance. So in this inquiry question, a key variable for a projectile in motion will be its initial velocity u. Not only will the magnitude of this velocity be important, but also the angle at which the object is launched from, and this is usually denoted by theta. Now, because the magnitude and direction of the velocity vector in the projectile will definitely change over time, it can be a little bit difficult to analyze this vector as it changes. Velocity vectors which are a lot more easier to use, however, are the velocity in the x and y components. So as we begin to analyze the motion of the object in the x and y directions, it's going to be really important that we are able to either construct a velocity vector from the x and y components, or as we're going to practice today, deconstruct our velocity vector into its x and y components. Now, there are a couple of ways of visualizing it. The diagram on the left is not one that we have used too much in the scope of this course, but it does come up quite often, or you may see it in some other courses. As usual, I'm going to break up our u vector into its x and y components by constructing a vector triangle, which is built by the sum of the x and y vectors. So when we have a vector statement like this, u is equal to ux plus uy. Essentially, we are doing a sum of vectors. In other words, a head to tail method to add up the ux vector and the uy vector. The resultant here, which is u, is going to be the vector that connects these two together. Now, because the x and y vectors are perpendicular to each other, we have in fact constructed a right-angled triangle where theta, the angle between u and ux, is the launch angle. If this is the case, we can use some simple right-angled trig to be able to write some equations for ux and uy, based on the assumption that we know the value for u as well as theta. So first off, ux is going to be equal to u cos theta, and uy is going to be equal to u sine theta. I've also included a quick solution to a very simple practice question which applies this concept. It reads, a ball is thrown at a launch angle of 48 degrees and at a velocity of 25 meters per second. We're asked to determine the horizontal and vertical velocities of the ball. In order to calculate this, I've first extracted all information from the question and presented it all diagrammatically. So the two key pieces of information that we have is that the magnitude of u is equal to 25 meters per second and that the launch angle is 48 degrees. From here, I've also written some formula to allow us to easily calculate for ux and uy. Substituting in, we've found that ux is equal to 25 times cos 48, which is equal to 16.7 meters per second. Given the data that we were provided with in the question, an answer to two significant figures is appropriate. Similarly, for uy, we substitute in our 25 and our 48, so 25 times sine 48 being equal to approximately 18.6 meters per second, which round to 19 meters per second to two significant figures. Thank you very much. In the next video, we are going to look at some assumptions that we need to consider when accounting for the acceleration of a projectile in the horizontal and vertical directions. But until then, have a good one.